Hi guys, I'm Jinghui. Today we are going to show you our research outcomes on the paper Backholding 5G Small Cells, a Radio Resource Management Perspective. The first half of the presentation will be presented by me, and then my teammate Xutao will take over the second half. Just as everybody knows, the upcoming 5th generation cellular technology is going to be a main trend of wireless communication development. In year 2020, the 5G tech is expected to have some features like 1,000 times higher data traffic compared with current cellular system, 10 to 100 times more connections, 10 times longer battery life, and so on. Therefore, to achieve these requirements, a bunch of strategies are to be used to improve performance of heterogeneous networks. Firstly, let's get some review on the evolution of small cells in cellular networks. The early form of small cells are microcell base stations, which have been used as kind of complement to macrocell base stations. The microcell base stations have lower transmit power, typically 10% of the macrocell transmit power. In addition, microcell has smaller footprints, lower capacity, and more flexibility, and more economic as well. Later, with the development of cellular technology, picocell and femtocell have evolved from microcell concept. The transmit power keeps decreasing. Accordingly, the coverage area also decreases. The capacity and coverage in a hotspot area can be improved by reducing cell footprint and increasing total number of cells. Therefore, more complex service scenarios can be supported. In addition to these cells, a repeater is a kind of relay equipment. It can amplify and forward radio frequency signal from a donor base station to a remote location. Secondly, we will look at some evolutions of radio access network architecture, which is also called RAN architecture. Since we have so many kinds of small cells to satisfy different kinds of application scenarios, the RAN is evolving to a multi-tier architecture. Network nodes with different power levels, capacities, and backhaul conditions are attributed to different network tiers. Another fundamental idea of RAN evolution for 5G is CRAN, which stands for Cloud RAN. In Cloud RAN, the baseband processing for many cells is centralized as baseband unit pools. With this technique, system performance is improved by coordination between cells. The system cost is also reduced due to the source pool. So far we have talked a lot about small cells or architecture stuff, but what are the relationship between backhaul and Z-sense? According to the author of the paper, backhaul is the most critical factor that impacts the RAN architecture and topology in reality, and consequently impacts radio resource management of 5G cellular networks. So what exactly the backhaul is? Let's consider the entire hierarchical network as a human skeleton. The core network would represent the spine, the backhaul links would be the limbs, the edge network would be the hands and feet, and the individual links within those edge networks would be the fingers and toes. So let's combine the RAN technology with which we have just mentioned and the backhaul network together. We will get this figure then. Basically, one mobile user communicating with a single cell can be considered as a local subnetwork, and then the connection between the cell tower and the rest of the world begin with the backhaul link to the internet service provider's network. So, here comes the problem. What's the backhaul solution for 5G system nowadays? We can simply divide them into two aspects, wired backhauls and wireless backhauls. For wired backhaul, fiber optics is the most preferable solution in terms of both capacity and delay. For long distance, typically larger than 10 kilometers, we basically consider optical transport network. For short distance, which means smaller than 10 kilometers, we consider unified passive optical network. The point-to-point fiber is also used as a complementary solution. In small cell wired backhaul, the copper wire is also used when bandwidth requirement is not that strict. Then when it comes to the wireless backhaul, it has some advantages like easy to install and cost efficiency. With line-of-sight communication paths, several gigabytes per second can be transmitted by free space optical communication or microwave. For non-line-of-sight wireless backhaul, they typically provide several hundreds of megabytes per second with point-to-multipoint connections. Another key technology for wireless backhaul is massive multi-input, multi-output. This technology uses a lot of low-power antennas to focus radiation power to a very small terminal spot by beamforming. Therefore, spectral and energy efficiency can be largely improved. Since just now we have studied the major backhaul solutions, now let's look a little bit deeper into detailed issues in a multi-tier RAN backhaul, which can be divided into 5 points. For the first point, if too many users in a small cell which have non-ideal backhaul, this may result in traffic congestion. Therefore, it is important to consider backhaul limitation in RAT selection. For second point, this is easy to understand because management of radio resource and backhaul links are critical to optimize the utilization of network resource. As for the coordination among cells in multi-tier RAN, they can mitigate interference and improve link quality, then improve the system capacity. Finally, the last 2 points. If the traffic demand is already known at each small cell, backhaul can be designed with minimized power and spectrum usage. The above 5 aspects are not independent and are often considered together. So based on these issues, we can have a better design in the system level so that the overall performance is improved.
In this section, I will introduce several existing resource management solutions and briefly talk about their limitations. These solutions can be divided into 3 aspects. Firstly, I will tell something about radio access technology selection and cell association. In homogeneous cellular network, the signal-to interference plus noise ratio has been used as the cell association criterion. However, in multi-tier cellular radio access network, since the high-power macro base station tend to attract more users, severe load imbalance between base station tiers will occur. Therefore, the communication rate in high-power macro base station is very low since the radio resources are shared by a large number of users. Accordingly, cell range expansion mechanism has been proposed to handle this issue. The CRE mechanism can offload users from high-power macro base stations to low-power small cells, which results in a more balanced load across the system. On the other hand, the cell association problem can be transformed into continuous optimization from NP-hard by relaxing the binary association indices, and that makes it mathematically more tractable. However, existing cell association schemes have not considered backhaul, especially small cell backhaul. For example, an aggressive macro base station offloading scheme will lead to overload of small cell backhaul, so we need to integrate the backhaul constraints in the cell association mechanisms. The second aspect is about interference management. The multi-tier radio access network of 5G is evolving into a user-centric architecture, so the ultra-dense small cell deployment has to abandon the cell planning and optimization approach for interference management and adopt denser spectrum reuse patterns to further boost capacity. Besides, combining the OFDMA and multi-input, multi-output technologies give finer resource blocks for scheduling. Because the OFDMA offers high flexibility in dynamic bandwidth allocation of sub-carriers, while the multi-input, multi-output technology adds spatial degrees of freedom to radio resource management and scheduling. This scheme is a promising solution to cross-tier interference management especially. The third scheme of interference management is resource partitioning. Resource partitioning and fractional frequency reuse mitigates co-channel interference. It divides the frequency band into non-overlapping subbands. Dynamic partitioning and allocation of the radio resources in both the frequency and time domains make good use of the spectrum and consequently improve system capacity. However, the limitation about these schemes is that they fail to capture the heterogeneous backhaul constraints. Therefore, much work has to be done to gain more insights into the interaction of backhaul and interference management. The third aspect is about shadowing and inter-cell coordination. In this part, I will introduce localized resource allocation and CRAN for centralized resource management. As the cellular RAN evolves into the tiered architecture, shadowing and resource allocation is often jointly considered with cell association, interference management, and energy-efficient designs. Centralized baseband processing and control of Cloud RAN is ideal for inter-cell coordination since it fully exploits the channel state information from all radio resource heads, while benefits of Cloud RAN come at the expense of increased capacity and overhead. Moreover, the bottleneck mainly lies in small cell backhaul. So that's all the existing resource management solutions I introduced. Then I will talk about a case study. It's about massive multi-input, multi-output based in-band wireless backhauling for dense small cells. In this section, we consider a two-tier cellular RAN consisting of one macro base station and some small cells to gain a general idea of how small cell wireless backhauling impacts radio resource management. The network geometry is shown as the left picture. In order to share the radio frequency components of the small cells to reduce hardware complexity, a small cell cannot transmit and receive at the same time over the same frequency band. So a co-channel reverse time division duplex and the soft frequency reuse framework is considered for interference management. In addition, simultaneous service and backhaul communications of the small cells are scheduled in orthogonal frequency bands. Since the small cell traffic has to be routed to the macro base station via the massive multi-input, multi-output wireless backhaul, and then to the core network, the best cell association is coupled with the varying backhaul constraint. If the same bandwidth allocation is adopted throughout the macro cell range, a unified wireless backhaul bandwidth allocation factor needs to be determined. This factor explains the backhaul and load conditions at small cell locations. Therefore, we build a radio propagation model with SINR-based cell association, small cell CRE with 5 dB SINR bias, and backhaul-aware cell association with unified wireless backhaul bandwidth allocation. The physical layer system model parameters for the simulation is shown in this table. Different numbers of small cells and mobile users are examined. The cumulative distribution functions of the user rates are plotted in this figure. From the curve of 10 small cells and 100 mobile users, we can find that the user rate with UWBA cell association is much higher than the user rate with SINR-based cell association. In contrast, the gain due to CRE is negligible. Besides, the number of small cells or the small cell density has much lower impact on the perceived user rate compared to the impact of the number of users. This is because of the bottleneck in the massive multi-input, multi-output air interface that is shared by all the small cells for backhauling. So that's the conclusion of this case study. Moreover, there are also some other open research issues and challenges of radio resource management with backhaul considerations for 5G, such as distributed backhaul-aware cell association, dynamic cell load-based backhaul radio resource management, and so on. In conclusion, we reviewed the evolutions of small cells and the cellular RAN architecture. outlined design issues and challenges for radio resource management with backhaul considerations, and the limitations of the existing schemes. Then, through a case study, we discussed performance gain with backhaul-aware radio resource management in a multi-tier cellular RAN. And finally, we listed several related open research issues. So that's all for our study on the radio resource management. Thanks for watching this video.